competition.
Thank you. Tough opening act to follow. I also want to just point out that some of you have seen me give a talk many years back on a related topic. This is not old wine in a new bottle. It's new wine in an old bottle in the sense that I've got the same model, but hopefully I have some newer results that I thought were worth mentioning. So just to get started, I really, myosin has been invoked enough times today and over the week that I shouldn't need to invoke him again, but this is being recorded for posterity, so I might as well go through this once. Basic question, how should a seller of a good auction it off? And we have at least one nice answer that we keep returning to, which is if there's a monopoly seller and he has n buyers, and these buyers are IID from a known distribution, and there's common knowledge of this distribution, and the seller wants to maximize expected revenue, then the problem is really nice. Well, it's actually really nice in one case. So what's that case? That case is when the virtual value of a buyer is non-decreasing in his actual value. And then myosin tells you that the optimal auction is a second price auction with a reserve that's easy enough to calculate. The other case, which we shove under the metaphorical carpet very often, is the case where that assumption is not satisfied. We help our case along by calling these regular distributions and these irregular distributions. But the basic point is that the optimal auction that comes out, to the extent that you believe the math, is weird. It involves something called ironing. It may misallocate the good. By that I mean that the optimal auction in this case may sometimes give the good to a buyer of a lower value, even though a buyer of a higher value is present and in the auction. So that sort of thing can happen, and that should be troubling. All the way off at the other end of the spectrum, there's another canonical paper that hasn't come up as much this week. So what's that paper? It's by McAfee. And McAfee considers a large market. So by a large market, we mean many sellers, each with a single item, many buyers, and all of these buyers are sort of have values IID from a known distribution. And the game he's thinking about is that each of these sellers is going to announce an auction. Each of the buyers is then going to choose which seller's auction to visit, and each buyer is going to choose this after knowing both her own value and all the announcements of all the sellers. And McAfee's result is that given everyone else, I've stated it as a best response. He states it as an equilibrium, but what's the best response mapping that he particularly points out? He says, given that everybody else has announced a second price auction with no reserve, any given seller's best response is to also announce a second price auction with no reserve. Now, part one, this means, of course, it's an equilibrium for everyone to announce second price auctions with no reserve. Part two is that McAfee doesn't make any assumptions on the distribution of buyer values. So the thing that was driving the distinction between sort of standard second price auctions and weird things in myosin is missing in McAfee. So of course, you're a young grad student or you're a young assistant professor. What do? You look to fill a much needed gap in the literature. So you ask, what should we expect in a monopoly? So here's the most obvious model you could write down. There's a seller with a single unit of a good to sell. There's m-1 other sellers, so totally m sellers in the market. And they also have a single unit of the same good. There's two buyers. We can talk offline about how to extend it past two. Some of the results will extend. Some parts that I hope to be able to prove actually don't extend. So they're all IID. The other sellers have committed to a second price auction with no reserve. Okay, so just all I want to do is to identify one part of the best response mapping, which is how should our distinguished seller, seller one, respond to a second price auction with no reserve. And what I'm going to do is I'm just going to try and repeat the Myasonian exercise in this setting and try to understand what's going on. The game is going to be like McAfee's, which is each buyer is going to choose which seller to visit after this buyer knows, the buyer knows both her own value and all the announced mechanisms. So we're going to look at an equilibrium in the subgame among buyers that is defined by the mechanism that was announced by me, by this distinguished seller.
buyers move simultaneously?
All the buyers move simultaneously, yeah. And the difficulty is, of course, that you don't have a nice linear program anymore. The optimal auction must account for how this incentivizes, for how the design of the auction incentivizes buyers to visit. And of course, before you think this is just an optimal auction design problem with a fixed outside option, note that the distribution of buyers visiting the other auctions depend on which ones are visiting me, which means that the outside options that the buyers have, that is what they would get if they went to another auction, also depends on the design of my auction. So everything is sort of endogenously determined, which makes it tricky. The main result I'm going to present today is, this didn't recompile correctly, for a seller competing against m-1 other sellers who have each announced second price auctions with no reserve. Necessary conditions for a second price auction, possibly with some reserve, to be optimal are that this term over here, this thing over here, this modified virtual value, is increasing in V. Now note that this is sort of convenient in the sense that when m equals 1, that is, I don't have any competition, I get back myosin, and when m equals infinity, this second term basically disappears, and I get back McAfee. Two footnotes that I should, caveats. First, I want to emphasize, so that I don't overpromise and underdeliver, the word necessary. I don't have sufficient conditions at this point. What I'm doing, as you'll see in a minute, is basically writing down a particularly hairy nonlinear optimization problem and using the necessary conditions there to get necessary conditions here. What I don't have yet is sufficient conditions. But the sufficient conditions for this class of nonlinear problems don't apply. So what I am in the process, this is very much work in progress. What I'm trying to do is use the same necessary conditions to rule out all other auctions, but all other mechanisms. But that's a slightly more involved exercise that we can talk about how far I got offline.
So just a quick question. Do you conjecture that this is necessary and sufficient, or do you actually have counterexamples?
No, I do not have counterexamples. I conjecture. Conjecture is such a strong word. I hope it's necessary and sufficient. I mean, things once you say conjecture, it almost becomes yes. Costas.
By second price, you mean second price with reserve?
I mean second price with reserve. So my best response could include a second price with a reserve, but I'm fixing all the other competing sellers to announce a zero reserve price auction. So I want So why do I need this? Well, because think about it. If I didn't fix the reserve, my other sellers might have a reserve price so high that they're not really competing at all. So I want to make the environment as competitive as possible. They're announcing second price with no reserve, and all I'm doing is I'm trying to make this. I'm trying to figure out my best response.
And your best response is with reserve?
With the reserve, yes.
Is M the same as K?
Yes. Sorry. Everything should be M. Sorry. That was a typo. That didn't go. Yes.
I know you're not conjecturing anything. But if you were to conjecture something, then the natural reserve is where this thing is set to 0? Or that's not the case?
No, what's embarrassing? Sorry?
It's not true for K equals 1.
For K equals 1, the reserve is exactly where this equals 0.
Now where this is equal.
Yeah. So, embarrassingly, I was asked this question and I still haven't figured it out. So I don't have I just don't know. I'm sorry. Okay. So that's the result. And if I had to give a grandiose overview of why you should care, it's that in a world where if these conditions are indeed the right ones, then basically the set of distributions on which you do weird things, that is things other than second price auctions, shrinks as competition grows large. So competition sort of takes away complexity in a particularly complex world. Okay? So that's a grandiose one sentence, whatever. What's the high level intuition? High-level intuition, let's go through two things we again know really well. So first, think of a world where there are a bunch of buyers, but it's a full information setting. So these buyers come stamped with their values on their foreheads. Okay? That's a really simple setting to optimize revenue. You just find the highest value guy, you give him the good, and you charge him his value. Okay? That's trivial. Now, in the Myosin monopoly setting, the setting with private information, the seller doesn't know buyers' values. By the revelation principle, he can just ask people for their values. But then, of course, the mechanism has to be incentive compatible. Incentive compatibility means that, roughly speaking, allocating a low-value buyer leaves rents for higher-value buyers. You have to give people money to tell the truth, right? You have to leave some money on the table to get them to tell the truth, because unlike here, you don't know what their values are. The virtual value, which we've all come to know and love, and everyone, or almost everyone in this room has played around with at some point, captures this cost of incentive compatibility. That is, it captures a value less a shadow cost of these incentive compatibility constraints. And the monopoly distortions are then because the seller would like to give the good to the largest virtual value rather than give the good to the buyer with the highest value. Okay? And when this sort of thing is non-monotonic, that's when you get the weird ironing stuff that Myosin talks about. So far, so good. The basic observation that I'm making here is that when you have competition, you have outside options. Outside options, I'm claiming, reduce the shadow cost of incentive constraints. Intuitively, to get people to show up, you'd have to offer those rents to them anyway, so you shouldn't double count. Okay? So roughly what you'll now have is the old virtual value plus some correction for the fact that you need to convince these guys to show up. Now, firstly, this term is positive. So you had V minus something plus something. So this thing wholly is less negative. So it's closer to true value. What a lot of existing analysis that I've seen tends to do, sometimes justified, sometimes not, is, including what I did in the previous incarnation of this work, is basically say, if you don't think too good, don't think too hard. So we would roughly want this whole thing to be increasing. So, well, one thing we can do is hope for this thing to be increasing and this thing to be increasing, right? To make this thing increasing, you say increasing virtual values. To make this thing increasing, you say decreasing density. What I'm trying to claim today is that actually, no, that's overkill. The structure of the competing auctions problem lets us say a little bit about the nature of these outside option, the Lagrangians of the outside option constraints, and that's going to help us get slightly tighter results than we had previously. Oh. Yes?
What you're saying, if both of those terms are increasing?
I'm saying if both of those terms are increasing, then clearly it's increasing as a whole. But that's, right? I mean...
But then you know that this is the best option? The second price was reserve? Or?
This is... yes, but for different reasons. I mean, you should treat this just as a high-level sort of... What some people have done in the past is started from this idea that you want some sort of corrected virtual value to be increasing, but then not thought more closely about what that corrected virtual value is. That's all I'm trying to say. Okay? And one final advertisement. Roughly speaking, one other cool thing, or somewhat cool thing that I had to bring in is that the seller's problem comes from a class of what are apparently known as, there's a thick book in my desk called mathematical programs with equilibrium constraints. So you have standard constraints, but then there's also a constraint that roughly the distribution of buyers visiting you or visiting the other sellers is not endogenous. It's not exogenous, it's endogenously determined. It has to be consistent with an equilibrium among the buyers given the mechanisms that the sellers have chosen. Okay? These equilibrium constraints are painful because if you want to use your standard first-order conditions, Kuhn-Tucker, optimal control, Pontryagin, whatever you like, constraint qualification is not satisfied. So you don't have necessary conditions anymore. So instead, I go deep into Google and pull out necessary conditions for optimality from the literature of MPEX. And as I said earlier, in progress is arguing that the same conditions are sufficient, but that's very much in progress. I have only limited. All right, so let's dive right in. What's the model? And model, 2 sellers for most of this talk, 2 buyers. Values are IIDs, draws from a distribution on 0, 1. Buyers can visit only one seller. The announcement, sellers are going to choose mechanism. Everyone other than one of them is committed to a second price auction, so it's really, real timing is a lot of seller 1 chooses his mechanism. Buyers choose which seller to visit based upon the announcement and their own valuations. And one important caveat is I am only looking at symmetric equilibriums among the buyers. So I'm not looking at equilibria among the buyers where the buyers' choice of which seller to visit depends on their name. Okay, only on, and then I just look at truth-telling equilibrium at each seller given the announced mechanisms, and the game ends.
Hey, Mallesh, the buyers can only visit one mechanism?
They can only visit one mechanism, yes. It's just a restriction. I have no idea what would happen if I didn't do that.
So Preston's paper has this repeated interactions. How do you connect this to that?
So at the heart of his paper, I mean, his paper is sort of, you're right, it's a complicated dynamic model. But at the heart of his paper is the following simple question, which is, take a large market and suppose the outside options for the other buyer, for all the buyers were given as if there was everyone else in the market had announced a second price auction and that so he just pins down, he pins down the outside options as if we were in equilibrium, then asks a seller to optimize treating those outside options as fixed, assuming that we're in a large market, so I wouldn't affect outside options. So I'm just talking, I mean, I've underrepresented Preston's paper, but this is sort of at the heart of his paper. To be fair, Preston didn't object to my, and if Preston objected, Preston would let me know that he objected. All right, fixing mechanisms of other sellers, we can think of the seller 1's problem as announcing a direct revelation mechanism and a visit rule. So what's a visit rule? It's telling I'm basically doing mechanism design, so I get to choose the equilibrium I like. All I have to do is I have to tell a buyer that if you're a buyer of value V, visit seller J with this probability. And the constraints, well, 3 constraints intuitively. 1, that the allocation rule A is feasible. So A is an interim allocation rule. It has to be something that I can actually promise to buyers. That is, I have only one good for sale, so I need to make sure that I can keep that promise. 2, I want incentive compatibility. And 3, I need, this is the new set of constraints that we haven't had to deal with in optimal auction design, which is that the visit rules constitute an equilibrium among buyers given the announced mechanisms of the sellers. Okay? So I can't pick any visit rule. I have to pick one that's an equilibrium. Okay. 3 helpful observations. First helpful observation is one that is actually from Preston's paper, which is you might worry that we have some complicated binomial or Bernoulli random variable determining the number of buyers at each seller, but you can actually make that simpler by just saying that if you're not visiting the seller, just show up at that seller and report 0. Okay? So roughly speaking, you're going to have a density at each seller that is the original density of that value times the probability with which he visits, and a whole huge atomic mass at 0. Okay? And this makes life much easier, and it also makes matters much easier in the sense that I'm just going to optimize over this, over achievable effective distributions. Good. The second, I hadn't invoked enough famous auction theorists yet, so this is the Matthews-Maskin-Riley border theorem. There's already been 2 talks on it, but here's the rough question. When there are n buyers IID from a fixed distribution, what are the set of feasible interim allocation rules? Well, the set of feasible interim allocation rules, Border finally cleaned this up. They had one direction. Basically, there's a set of linear inequalities that define whether or not a interim allocation rule is feasible. And by feasible, I mean that there exists an ex post allocation rule that allots only one good at any given profile ex post and results in exactly that interim allocation rule. And an aside that's going to be useful is that this is a convex set. It's actually a polytope. It has a bunch of corner points, and we know what those corner points are. Those corner points are effectively, Young already introduced them, but basically they're what Border calls hierarchical allocation rules. So basically there's a ordering on types, and you give the good to the buyer with the highest priority according to that order. The reason this is going to be useful is because this gives you a low-dimensional, easy to describe, easy to work with way of dealing with the set of all feasible allocation rules. Okay, so this is going to span the set of buyer strategies in a helpful way, and that's helpful because, of course, the distributions are endogenous, so it doesn't help if we just describe what the mechanism does at different distributions in the interim space. Okay. Is that a question or just no? Sorry. Now, incentive compatibility is actually the same as before. So because I'm pinning down, I'm doing mechanism design, I'm picking down, I have to still have that the mechanism is incentive compatible for the distribution of buyers that visits me in the equilibrium that I'm asking buyers to choose. So in particular, given that seller 1 offers a mechanism with interim probability of allocation A1, the pricing rule is going to be pinned down in the standard way. And the interim surplus that of a buyer visiting this seller is pinned down. Okay? So these things are pinned down in the way that they always have been. Since everybody else is running a second price auction, and the we have this notation for the effective distribution, we know what the probability a buyer wins at seller J is. It's the effective distribution to the n-1. This n-1 is exactly where I need n equals 2 for some calculations that are in progress, because at n equals 2, this becomes 1, and therefore the allocation probability is linear in the visit things. Without that, it becomes a messy polynomial that I don't know how to work with, but that's neither here nor there. And by the same argument, the interim surplus of the seller, if she was to visit the other of the buyer of value V, if she was to visit seller J, is given by SJV. So now we can just write this down. We have this. We have this nice. We have something that looks kind of close to the Meyerson problem, but there are a few changes. So this first, I'm maximizing expected revenue, but it's no longer with respect to a fixed distribution, it's with respect to a distribution that's determined endogenously. These constraints look the same as before given the distribution, but I now have an additional constraint on the distribution. That is, that if I'm telling a buyer to visit a given seller with positive probability, the surplus she gets at that seller has to exceed the surplus she gets at any other seller. These additional constraints are what make this problem fun. And of course, we know what all these terms are because of the analysis we just did. Bad news, there's still no maximum principle for this class of problems. I actually mailed the person who thought they had it, and they said they still have some errors, so they're working through with it. But what they do have is a version for finite problems. So let's discretize the space of buyer values. What do I mean by discretize the space of buyer values? I'm just going to consider values on a grid. Move the mass of each interval onto the lowest point on the grid, and consider the optimization problem for the discrete problem instead. So I now have a standard finite dimensional optimization problem. Firstly, existence holds. The discretization problem has a solution. Could probably use some fancy topology and pull it out for the continuous type, but not done with that yet. And there's no point doing that without a maximum principle anyway. So basically, what's the idea? Remember we said we had these polytope that described the feasible region. You can think of each mechanism as just a probability distribution over all the corner points. So as a convex collection, so this is a finite, so the finite set. Also, the feasible region is compact because it's basically closed and bounded. So you're optimizing a continuous function on a compact set, which is great. Optimum exists. We can all go home happy. This is flashed for posterity. These are the conditions for a, so these are the novel conditions. These are the equilibrium conditions written as a complementary slackness constraint. The necessary conditions for optimality basically go ahead and ignore these complementary slackness constraints, and instead the multipliers on these proper constraints are, they don't have a sign on them. That's basically, whereas standard Kuhn-Tucker conditions, since these are proper constraints, these would be non-negative multipliers on them. So we've written the Sellers problem as an optimization problem. We've argued that it's well defined. We have a maximum principle. Well, what's left? We have to construct a candidate optimal, use the maximum principle. So let's go ahead and do the first part very quickly. It turns out that we actually know what the equilibrium among buyers looks like when two or multiple sellers announce second price auctions. So let's just quickly go through this thought experiment. I've announced a reserve price of 1. You've announced a reserve price of 2. What's going to happen? Everyone below this, well, it doesn't matter what they do. Everyone in this interval obviously has to come to me because they wouldn't even be served if they went to you. If you were just slightly above this reserve price, the buyer, if he showed up at the seller 2's mechanism, he'd get basically no surplus, because even if he won, which he'd win with low probability, he'd be paying almost all his value in the form of the reserve price. So actually there's another interval, and that whole area is visited. These guys visit seller 1 uniquely. What's important is that there's a whole upper interval on which the buyers are indifferent between these sellers, and they randomize 50-50. Okay, so that's the equilibrium shown by Berger and Sakovich and Peters and Severinov, who both considered competition in second price auctions. For us, what's relevant is that means that if you were to announce if the other seller was announcing a second price auction with a reserve price of 0, and you announced some second price auction, what they're telling you is that there'd be some upper interval on which these individual rationality constraints bound. And this is the this is just the part where I have no real intuition to offer you, which is you can work through the system of necessary conditions and can figure out the multiplier corresponding to these equilibrium constraints. I have tried to come up with a story that might justify this, and I have not. So all I can tell you for now, until you can verify the paper, is trust me. So trust now, verify later. That's what I got. And as it is for m greater than 2 sellers, it works out similarly. Now, I've shoved a bunch of things under the carpet for the purposes of a 30-minute talk, which is that discrete types have a slight degree of freedom. So the formal theorem is actually even slightly weaker than I advertised, which is, suppose that the distribution is such that this thing is not decreasing, then you've got a fine enough then there exists a fine enough discretization such that announcing a second price auction with any reserve is not optimal. That is, second price auctions the class of second price auctions, none of them can satisfy the necessary optimality conditions when competing against m-1 sellers who have announced second price auctions with 0 reserve. So it's basically that spiritually these are the right necessary conditions, but that's life. Remaining steps, hope that it works out in the other direction. Lots of famous people have done lots of great work in this area. Some people have gone off straight to the large market. If you want to be really, really grandiose, you can say that this problem is at least as old as Bertrand Edgeworth, which dates back to the a century or more. But it's really among a class of questions that is just trying to endogenize both sort of how the goods are assigned and how the goods are priced in a competitive model. And I'm not going to, with very limited time, I'm not going to hold you up from lunch any further. So in conclusion, I'd like to say that there's less work than one might hope. Given that competition is all around us, we'd hope that we understand more about mechanism design in the presence of competition. And the issues are basically that there's issue. It makes for very hairy optimization problems, and that we don't always know how to solve these optimization problems. But there's light at the end of the tunnel, and I mean, you know, you've seen talks by Brendan, and for those of you who've been around, you've seen talks by Eva and Vasilis and so on that are trying to get at this from a different from different tools and from different sides. But basically, even though these models with competing markets and so on are complicated to analyze, they may lead to simple auctions as the equilibrium result, which would be very satisfying aesthetically. So that's all I got.
Two sellers, two buyers. Is there a pair of reserves such that running second price with reserve R1 and R2 is a Nash equilibrium?
No. There is, so that the reference for that is Berger and Sakovic. There is no asymmetric pure strategy equilibrium in second price auctions with reserves, even if the distributions there is even if the distribution, it's worse than that. So even if the distribution is as nice as you like, for instance, the distribution of buyer values is uniform 0, 1, you can't even analytically write down what the mixed strategy equilibrium is. So not only is there no pure strategy equilibrium, there's no nice mixed strategy equilibrium to do other economics with. Yeah. Yeah.
How about multiple sellers having the same reserve?
Not an equilibrium. Unless you go literally to the large market, in which case McAfee tells us it's 0, and in which case you can interpret the results of Peters and Severinov and others. Oh, I should step back for a second. So you can interpret those results as saying that it's sort of an epsilon Nash to be sort of close to 0. One sort of class of results that I should have also been more careful to. Suppose I move the support instead of over 0, 1, I'm sort of really thinking of a C, C plus 1 support. For C large enough and for some distributions. Then there might exist an equilibrium, and this is the paper by Virag that I cite on my previous slide. So there's a paper by Gabor Virag, who's at the University of Toronto, where he shows that there is an equilibrium in pure strategies among second price auctions, but where both sellers charge a reserve price below the lowest point in the support. Okay, so I'm sort of discounting, giving a discount to buyers to compete them to show up, and that's, but yeah.